But of course, we always have this kind of huge picture of the challenges related to energy. And this was taken from a slide by the US DOE. So we do have, of course, the challenges related to generating energy without any emissions. So that could be either nuclear power sources or wind and solar, which are renewable energy sources. Then, of course, we have to deal with how we store this energy, which is the main focus, I guess, of your work. And of course, in the end, we have to kind of utilize this clean energy. And if we look at into the utilization, this is actually very critical and not as much looked at as generation from renewables and also energy storage. So if we think about it, the petrochemical industry is a huge industry. It pretty much makes everything we live on. So this is the predicted size in billions of dollars in the change in the petrochemical market over time with relation to specific molecules that are produced. And you can see, of course, ethylene dominates. It makes a lot of things like polyethylene, methanol also. And really, it touches on pretty much every single component of our life. I should definitely say, fuels and energy is pretty obvious, but cosmetics, agriculture, food industry, clothes industry, textile, construction materials, these are all actually officially part of the petrochemical industry. So it makes it really important that we are able to utilize all of this energy that we generate, or be able to somehow generate clean energy and utilize it directly in the industry. So I'm going to try and focus a little bit on the utilization process today, just to kind of get an overview of the things we do in that field. So one of the things that everyone likes to talk about is utilization of CO2. So we emit CO2, we somehow collect it and purify it. And then, of course, we can reuse it, hopefully. So kind of close this anthropogenic carbon cycle produced by humans, obviously. So CO2 reduction is not a simple process. It looks really simple when you just look at the chemical equation. So CO2, some hydrogens, and or protons more like it, and some electrons produce products and water. But if you actually look into the literature, so over here you can see this is taken from a review that pretty much kind of encompasses all of the different pathways where you can go from CO2 to really very specific molecules. So CO for one, or methane, ethylene, and even ethanol. And these are, of course, very critical and important molecules. But even just for very small steps, you can see that absorption on the surface is a critical aspect over here. How the molecule absorbs, what is the absorption site, how it can couple and produce our products. And if we look into something, I would say even simpler, because CO2 reduction, I mean, all these chemical pathways are crazy. If we look into something even simpler, so hydrogen production, so that we can then utilize it in fuel cells. So this is actually kind of a distribution of the costs of fuel cells. So these are all the components together. You can see the fuel management, air management, thermal management, and then the stack price, which is pretty much 50% of all the cost of the fuel cell. But in the stack, we have a variety of different things. So seals, the bipolar plate, membranes, etc. But the biggest component is, again, 51%. And it's the electrode. Why? Because the materials that compose the electrode are, of course, made of precious metals, such as platinum, iridium, ruthenium in commercial fuel cells. So we kind of want to try and avoid these and look for new materials. And in this case, it's really not even as complex a reaction. It's definitely considered a complex reaction, especially the oxygen evolution side of the reaction, where we're just taking the water and splitting it into oxygen and hydrogen. But the anode reaction, which is the oxygen evolution, involves 4 electron and 4 proton coupled transfers. You can kind of see a cartoon here on the side. The minimum overpotential for these reactions is 1.23 volts, but of course, we know that that's not the real case, and it will never be 1.23 volts. So to solve all these issues with catalysts, we kind of look into a new direction. which is multinary materials. And by multinary, I mean many element. We usually look at 4 elements minimally, and we try to go up to more, although I will show you some results today with less elements because they're proof of concepts. So we generally kind of work in this cycle. We have some machine learning guidance. We then, which helps us predict or correlate our data and things that we want to understand about these materials. We then try and synthesize them using high throughput and characterization synthetic methods. And of course, once we find these materials of interest, we go in depth and study both catalysts, but also materials for photovoltaics, which is actually also still very important because as much as silicone works well, and it works fantastically great, I have to say that if you would put the option of making a chip or a PV device out of silicone, most everyone would go for a chip and not for a PV device. So we do need to find alternatives or things that can assist silicone so we can reduce the amount of silicone in PV devices. And a small question that can arise, I guess, in this relation is, why do we actually want to use multinary materials? Well, there are several reasons. First of all, as a proof of concept, so this is a figure that shows the critical temperature of high TC superconductors with relation to the number of elements. And yes, I know about the archive publication. I think there's no one who doesn't know about it, but I'm pretty sure it's not been proven to be actually real yet. So we'll stick with these oxides and different kind of mixed structures. So the higher amount of elements that we have, the higher critical temperature we're able to achieve for these superconductors. So that means something is going on over here when we have more elements, which leads to synergistic effects that enable these special properties that are otherwise not possible, for example, with mercury. And another thing is that if we look into the amounts of elements, and this is elements used in the semiconductor industry over the years, so you can see that by the 80s, we were using 11 different elements, but now in 2000s, we're already using more than 61 elements actually. So it's really critical to kind of understand how all of these elements work together and how they interact, what their effects are on one another, in order to really be able to utilize these materials to their maximum abilities. And if you further think about it, actually, so if we just, let's say have 60 feasible or viable elements from the table of elements that we can possibly work with, and we just do basic combinatorics with like n and k factorials, then we'll end up, if we have, let's say, 5 element combinations with 1-to-1 ratios, then this actually leads us to more than 24 million compounds. And that is really significant. So this is a huge parameter space that no one has been studying and no one has been looking into. Some people have, of course, but not at the level that we should be looking into it. So these are some of the main driving factors and motives behind the work that we do. So today I'm going to try and focus a little bit on the guided machine learning aspects and high throughput synthesis and characterization and different synthetic methods that we've developed for this. So let's get started with the high throughput synthesis. I'm assuming many of you know about combinatorial material science, but just a brief overview. This is generally considered a high throughput synthesis method where we have large area samples, which are referred to as material libraries. So here's an example of a binary system where we have just an A and B components, and we go from 100% A to 100% B, and all of the different different compositions between the sample, between the components A and B, all over the sample. And of course, for this, we need to go through high throughput characterization and go point by point really and investigate every single point, or however many predetermined points that we decide on, with dependence on some pre-existing matrix that we choose. So that's the gist of combinatorial science or high throughput science, however you want to call it. And it's been heavily used already since 1985, I think the first publication came out in Science about it. And shape memory alloys were discovered using it. Photoluminescent materials were discovered using this method. So it is a strong method and very beneficial method for actually obtaining new materials and compounds that we want to look into. But one thing that I should mention is that generally speaking, the most focused on aspect of high throughput synthesis are compositional changes. So we're looking at changes in compositions or variations or gradients in compositions along this materials library, but we're not necessarily looking at other stuff. Yes, it's true that people have also studied temperature or thickness changes, but these are usually the minor studies and not so much the major studies. Compositional changes is the focus. And for us, as people who do catalysis, it's also really important for us to look at the shape. So our surface area, the nanostructuring, nanomorphology, and porosity, things like that. And control of shape on the nanoscale is possible. And it's specifically possible using physical vapor deposition methods. So in order to form material libraries, the standard method for doing this is, for example, sputtering, a physical vapor deposition method, which is continuous and very easy to make these material libraries. So we can control nanoscale also using physical vapor deposition to form a variety of different types of structures. And this is done using glancing angle deposition, which I will explain shortly. And using these techniques, you can really form quite a wide variety of nanostructures, so helices, barcodes, zigzags. And these nanostructures don't necessarily have to be composed of a single element or a single compound, but they can be kind of mixed, forming junctions or a variety of different shapes. They can also be intermixed, so you can form core shell-like structures and quite a large variety of controlled nanoparticles. So what is this glancing angle deposition? This is the approach that we use in usual PVD systems. So this is just an example of an E-beam evaporator, electron beam evaporator. What you can see is that you have your source material, you have your electron beam that's focused onto the source material. This heats the material up and forms a vapor, which is then deposited on your sample, your wafer, your substrate, which is rotating on the other side of it. They're all, of course, directly parallel to one another. In glancing angle deposition, there's a huge difference. So your source material versus your substrate or your sample is tilted to very high angles. And these are oblique angles, which is this alpha angle tilt. So this alpha angle is versus your source normal and your source material. So you have substrate and source material. This angle between them forms this alpha. And this tilt has to be between 80 and 90 degrees to be considered glancing angle. Anything from 0 till 80 is oblique angle deposition, just for clarification purposes. So what happens when you tilt your sample to high angles? Well, you have some initial vapor flux gradient, vapor flux coming in onto your sample. And of course, samples are never straight. They always have some kind of tiny roughness to them. And that is where your initial seeding points form. And this happens within the first few nanoseconds of the deposition. And these seeding areas that form are actually the little self-shadowed regions that then interfere and kind of block the vapor flux gradient from coming in. So any of these seeding layers are pretty much where your material will be deposited, and nothing will be deposited behind them. And that is essentially what controls the formation of these different nanostructures during glancing angle deposition. So you can really form quite a wide variation of different types of structures, as I showed you already before, but they can go from nano size till micron size, which is very significant, I have to say. So high control, it very much depends on the system. And generally speaking, this is done in E-beam because you can have a really large distance between your source material and your sample, which allows for vapor collimation, which improves the nanostructuring. So what did we try to do? What we tried to do is see if we can create gradient samples, both in composition, but also in our surface nanostructuring or in our nanomorphology in general for all of the different films that we form. So these are not just flat thin films. What we were trying to do is form high throughput nanostructured thin films. And to do this, we used a variety of simulations, but we're not going to go into that. And pretty much we put a barrier in front of our source material. There's a dependence on the barrier distancing from the opening of the source and the barrier height, which forms a vapor flux gradient. And this we did by placing two source materials, one across from each other with their own individual barriers placed to form the vapor flux gradient. Then we deposited two materials, rotated by 120 degrees to deposit two more, rotated again to deposit two more, and then we end up with an octernary elemental materials library. So some of the source materials had more than one element, as you can see, barium titanate or lanthanum oxide. And these materials were actually chosen because they had shown high activity individually, each individually, for oxygen evolution, which is what we were trying to use as a reaction for proof of concept. So, of course, if we look into the compositional spread, we are expecting to see differences. So indeed, we do. These are composition heat maps of the different elements composing the materials library that we formed. So you can see nickel has a very nice gradient from 70% to almost zero, cobalt the same, etc. Some materials we had some issues with depositing, but these are known things because the materials degrade over time. However, we still decided to use them. So now that we have compositional gradients, we asked ourselves, do we actually form different types of nanostructures in this single one-shot deposition process? And indeed, we really do. So we go from L-shaped kind of nanostructures on the molybdenum side through some intermediate down to, we like to call these bone-like structures, but anyone can imagine whatever they want on the cobalt side. And then match-like structures on chromium through two types of intermediates down to kind of these zigzags on the nickel side. And each of these nanostructures also has its own different type of composition. So you can see that these L shapes are composed, the long side is composed of chromium, and then the top side is composed of cobalt. The nickel, the edge parts of the zigzag are composed of actually nickel. The rest seems to be a lot of molybdenum. But of course, all of the different types of materials are here. Some like to very much interdiffuse between the layers. So the tantalum, barium, and lanthanum interdiffuse heavily. But the nickel, for example, likes to cluster, as well as the cobalt. So we were very happy to see this because this was the first time that anyone was able to make both compositional and nanostructure gradients in a single shot deposition process. So this is direct without breaking vacuum, just putting the sample in and letting it go. Of course, we also, for the sake of catalysis, wanted to investigate the different properties of this library. So I'm just going to give you one example of the things we looked into, and this is oxidation states, which are, of course, very critical. So for some of the elements, we get the standard stable oxidation states. For others, we get two stable oxidation states, but well known, so similar maybe in the cobalt to the CO3O4 phase. What we do see that's very interesting is in the case of chromium, we have actually a gradient that goes between chromium +6 and chromium +3. So chromium +6 is the less stable oxidation state versus the chromium +3. And what we see over the evolution is that we get more of the unstable state as we go farther away from the chromium source, so the chromium edge of the materials library. And the same thing actually happens for nickel. So we get both nickel +2 and nickel +3 that changes with the gradient in position. And what we attribute this to is the fact that these elements are situated within so many other elements, and they're all sitting in different levels of oxidation and reduction, if you can think of the oxidation reduction scales that we know for electrochemistry. And what we believe is that this actually helps to stabilize these different oxidation states, which would lead to really interesting activities, hopefully. So of course, once we investigate these materials and look at their characteristics, and we see that they're both compositionally varied and also nanomorphology varied, and as well varied in oxidation state in our case, then we looked at the electrochemical characterization. So these are just LSVs from the edges. We did, of course, full material library scans. But you can see really just from the edges that there really is almost no variation. I mean, this is within the error limit, of course, between the different edges, which was quite surprising to us because we thought to ourselves, well, we have variation in nanostructure, we have variation in composition, we should see a difference. And we get pretty much, I mean, this is just 25 points along the library that I plotted here, but we pretty much get similar overpotentials throughout. And after really investigating this in depth and trying to figure out if we were having issues with the reference electrode, well, it actually turned out that if we looked at the CVs, the most active materials seemingly was nickel. So each and every one of these peaks is associated with oxidation of nickel. So we then looked into the XRD of this system, and what we saw is that in every single point, we actually have nickel oxide that forms. And if you recall, nickel oxide prefers to cluster in different connecting points throughout these nanostructures. So what essentially we're doing is we're forming stabilized nickel oxide nanostructures, which are showing the activity over here. So we thought to ourselves, well, what will happen if we are not actually doing anything with this library and it's just nickel oxide that's active? So we made a reference library, and this reference library is composed of nickel oxide nano-clustered nanorods, a lot of nano there, sorry. They look pretty much like this. And you can immediately see that when we measure them, the overpotential for the nickel oxide nanorods, so this sample over here, is much higher, 90%, 90 millivolt higher, sorry, than our materials library. So this is significant. And what we understood from this is that even though we have nickel oxide as the source, it's actually the nickel oxide nanoclusters that are embedded within our nanostructures, which allow this ability for much better activity. So if we just have pure nickel oxide nanoclusters in nickel oxide nanorods, they're not as active as the ones embedded in this special nanoscaffold. And indeed, we also made a sample without nickel to see the effects of composition as well. So you can see there is a variation in composition, more than 100 millivolts between the different edges, which is what we expected to see. So there is a compositional effect. But if we look at the overpotentials of the library with the nickel versus the library without the nickel, we can see that these nickel oxide nanoclusters are highly, highly active, and they really play a significant role, but they only play a significant role because we have this special nanomorphology, nanostructuring, which enables their higher activity. So this is not possible without it, of course. And in this relation, we were also thinking of developing other methods to make different types of nanostructures with GLAD. And one of the things that we were working on is nanoporous metals. And nanoporous metals are, of course, very significant. They have extremely large surface areas and great conductivity. They have activity for optical plasmonic properties. So they're very good, but of course, also they have very high catalytic activity for CO2 reduction, for methanol oxidation. And what we were trying to do is see if we could maybe use glancing angle deposition to make a direct kind of method to actually be able to form these nanoporous metal structures without having to use all of the components that are usually used, which the conventional synthesis methods have really a lot of drawbacks, I have to say. So a lot of times people use these template-assisted electrodeposition methods, which are fine, but then you have to end up etching out to remove the templates, which are, of course, a lot of times corrosive environments. And one of the main methods that's used is dealloying, where you start off with a master alloy, which is usually gold and silver, and you etch out your silver. The drawback here is that, again, you have to use harsh environments to etch out your silver, but it's also difficult to make materials that are corrosive because you'll be etching them instead of actually forming your nano structured metal mesh things. So pretty much you also end up with impurities, and that's of course something that we don't want to have. So we want to be able to have pure materials that we can investigate and study. So what did we do here to try and solve this? So we start out with our substrate material, which on top of it, we deposit a PMMA film just by pure spin coating, very simple. This is a thin film, several microns thick. On top of this, we do glancing angle deposition. And the benefit of glancing angle deposition over here is that it forms a very high density layer of nanoparticles. So these are maybe 20 nanometer nanoparticles, no more than that, of course, even smaller ones. And then the next step is we do some sort of plasma etching, and we actually end up with these nanoporous metal films. So these nanoporous metal structures. So what in fact is happening is more interesting is the plasma aspect. So this plasma effect, I'm not going to go deeply into the mechanism over here, but it pretty much involves the initial stage where we have the ions that start attacking the PMMA and of course reducing it. At this point, the metal mobiles become a little bit mobile due to some internal thermal effects and the movement and etching of the PMMA. And because we have low interfacial energy between our ions, between our metal nanoparticles and the PMMA, so the PMMA shrinks, but the metals also shrink together with them, forming islands. Then eventually the metals start coalescing. The PMMA is completely removed. At this point, we have high interfacial energy between our silicone substrate and our metal. So they do not move anymore, and they actually form these nanostructures. And what's nice about this is that we can really do pretty much any metal that we want. So we can form these nanoporous metal films, using them even for sensitive metals such as iron and nickel, which could etch out with some of these corrosive etchant environments. We can also, using the different plasma conditions, control the pore sizes and the tunability of the ligament sizes, so shapes and kind of structure. And also we can make 3D layers of these different types of nanoporous metals. So pretty much we're covering very thin 2-3D layer, and we can really, it's a really robust technique. And what's very nice about this, because of the mechanism of the way they coalesce, we're forming high curvature sites, actually, which are usually known to have high activity for catalysis. And you can see really lots of different types of grain boundaries. This is related to the coalescence mechanism, which is generally not seen for metals, for example, that go through the dealloying method. And we really have a variety of different planes that you can see over here. And what's interesting is that before our plasma treatment, we actually have some gold oxide on the surface, but after our plasma treatment, when we move from nanoparticles to these nanoporous mesh films, we end up actually having just pure gold. So besides forming this mesh structure, we can also form, I mean, this is just an example of a gold mesh film, sorry. We can also purify further our surfaces. So as a kind of test subject, we went with gold, as you can see over here. And we looked into the stability under electrochemical working conditions, which is, of course, critical because electrocatalysis is done, of course, under bias. So first, we started out with looking at acetic media. And you can see from our first cycle to the second cycle, there's only one reconstruction, first to second. And then the rest of the time, the surface pretty much remains the same over the scans. So this is actually very significant because we don't get a lot of surface reconstruction, which means that we have high stability over time. And if we look at the surface area evolution over time, we only get a reduction of 15% in the electrochemical surface area, which is really nice given the high porosity of these materials. And if we compare this actually to the dealloyed material, what you can see is that, so these are the first 4 cycles that I took from literature. And you can see that from 1 to 2 to 3 to 4, you have significant surface reconstruction, which is something that just does not occur here in our case. Why this happens in the dealloyed situation is because you have significant additional leaching of silver ions from the surface, causing reconstruction of your gold surface. And that's why this surface is considered less stable. We also looked, of course, in basic media. So we used KOH and alkaline solution and cycled it over time. And again, very, very minor surface reconstruction between the first and the second scan. Of course, we have a reduction in the electrochemical surface area. But in this case, in alkaline media, it's actually related to the fact that you can see this peak over here. This peak is associated with adsorption of OH ions on the surface of gold. So essentially, this oxidation starts about 150 millivolts lower than acetic media. So in general, gold is less stable in the alkaline solutions. So this just makes the material more susceptible to coarsening over prolonged cycling, which is why we see higher reduction in the electrochemical surface area, but this is quite commonly seen. And another thing we did to kind of try and understand how stable our surface is UPD measurements. And this is just measuring initially without any pre-treatment. So just the direct sample taken as is from the synthesis chamber. And you can see that we have a variety of peaks. These Peaks over here is associated with defects in the 111 phase. And this peak over here is defects associated with the 110 planes. And you can see that we have the 111 and 110 that mainly seem to have activity. And if we look at acetic and alkaline treated nanoporous gold mesh films, so this is, we treat these and then we do the UPD on them, you can see immediately that we're reducing the amount of defects, but we still maintain these active sites in 111 and 110 planes. And if we compare the areas of these different peaks, you can see that the 111 peaks completely disappear after treatment, but we still remain with these 110 defect sites, which is not a bad thing. We want to have defect sites and we want this high curvature and defect sites because they provide more catalytically active sites. So we then tested this for methanol oxidation reaction in 0.1 molar methanol. And you can see nice activity for it, comparable to, of course, other media that's tested, so other types of gold, and also very low reduction in our electrochemical surface area before and after the methanol oxidation. And if you look into the TEM images of the different ligaments and concave structures, you can see that we still have these very high curvature areas. We still have a lot of different grain boundaries, even though there is some minor surface reconstruction, as we saw before, but it's so minor that it really doesn't even come into obvious light if you look at the TEM. What's really nice about this is that pretty much this can be used as a reference benchmark material for anyone who wants to try and look, for example, in the case of gold, how the different additions of impurities affect the gold activity. So you don't only have to look at silver anymore. You can try putting in copper, you can try putting in iron, you can try putting in nickel, and seeing, you know, the different amount of dopant levels or impurity levels, how they affect the activity. So our material is really, really pure and really clean, and that's why it's a significant benchmark reference material. And it can be done for any type of catalytic reactions. We're also looking into it right now for oxygen evolution reaction. And furthermore, we're now already building mesh structures based on oxides. So we have lanthanum nickelate structures, and you can see they're quite peelable already and very nice, which we plan to test for a variety of catalytic reactions. And you can actually think of other different directions to go, such as transparent freestanding films. So this is actually a thin film of this nanoporous mesh structure, which is just floating around in acetone, and it has quite high transmittance. So this can also be used for a variety of different ideas and concepts. So that kind of closes the synthesis aspect of the talk. And since I figured it would be a nice introductory way to my lab, so I hope you can see the videos. I don't know how well they go through on Zoom, but these are some of our high throughput synthetic methods. So we have spray pyrolysis, pulse laser deposition with 6 material sources, RF and DC RF sputtering. I should update it because it's now DC RF sputtering with 6 different material sources. We have thermal evaporation with 4 sources, and these are all simultaneous, of course. We have a glancing angle deposition system, which will have 6 simultaneous sources with 10 options of materials in the chamber, and that's under construction at the moment. And we also have a variety of different high throughput characterization techniques, so current voltage, optical, electrochemical methods. Our electrochemical methods are now coupled to GCMS in operando. We're planning to further improve this to ATR, FTIR measurements of the solution in situ, resistivity scanning, and pretty much any kind of physical characterization that you can think of, we either have in our lab or is available to us in our infrastructure. So to finalize, some take-home messages. Hope I convinced you that multinary materials are the interesting pathway to go, specifically for catalysis and PV. I'm sure for batteries too, because most of battery materials are actually already multinary when you think about it. Glancing angle can really be used for making gradients in nanostructures as well as composition, and we were able to show this for the first time, and we now have full control of this ability. And glancing angle deposition can also be used to make a variety of different other types of nanostructures, which of course is very important because now we can tune these as well and make multinary nanoporous mesh-like structures and think of other structures that we can make in the future. I hope I also convinced you that for machine learning, features are extremely important and you really need to choose them properly. But even if you have crappy features and crappy data, you can still actually be able to learn a significant, interesting law, even by basic kind of machine learning tools, without having to think too much. But if you look at your data and your feature importance, you can really understand what's going on. One last thing, we are hiring. We have a few positions for PhD and postdocs, some MSc, but usually people don't travel for that. So PhD and postdoc positions, some are available. Please contact me if you're interested. And with that, I would like to thank all the group members. You saw work today from Johannes and from Yuval, who worked hard on some of the stuff over here, our collaborators from all over Europe and Israel, and our funding resources. And of course, thank you very much for your attention.